For 165 million years, this planet was not ours. Before the first human city, before the first cultivated field, before the earliest stone tool was shaped by a deliberate hand, the Earth belonged to something else entirely, a world of staggering complexity, a world of systems and rhythms and hierarchies of power, built and refined over spans of time so vast that the entire human story, from the first chipped flint to the present moment, occupies less than a fraction of a single percent of it. And yet that world, the world that came before us, has been reduced in the popular imagination to a handful of roaring predators chasing screaming prey across an empty landscape. That is not what it was. That is not even close. The first thing to understand about the dinosaur world is that you would not recognize the planet. Stand anywhere on Earth today and look out at the horizon. The continents beneath your feet are not where they were 150 million years ago. The Atlantic Ocean as we know it did not exist. North America was separating from Europe along a rift zone still in its early stages of formation, a slow tearing apart of rock and mantle that would take tens of millions of years to complete. South America and Africa were pulling apart, connected only in the far south. India was an island continent, drifting free in the middle of what would become the Indian Ocean, still millions of years away from its collision with Asia that would eventually push up the Himalayan mountain range. If you could observe the planet from orbit during the late Jurassic period, roughly 150 million years ago, you would see something fundamentally alien to modern eyes. Shallow inland seas covered enormous portions of what are now dry interiors. An extraordinary body of water called the Western Interior Seaway split North America down the center, creating two separate landmasses. The western portion, known as Laramidia, stretched from what is now Alaska to Mexico. The eastern portion, called Appalachia, was a strip of islands and coastline. These two landmasses had different dinosaur faunas, different plant communities, and different ecological histories, separated by hundreds of miles of warm, shallow sea. The climate was warm everywhere on Earth. There were no permanent ice caps at the poles. There were no polar ice sheets. Average global temperatures were perhaps 8 to 15 degrees Celsius warmer than today, sustained by atmospheric carbon dioxide concentrations estimated at 3 to 5 times higher than pre-industrial levels. The greenhouse effect was real and continuous, and the result was a planet that was, from pole to equator, dramatically warmer, wetter, and more uniformly habitable than the world we occupy. There were no grasslands anywhere on Earth. Grasses had not yet evolved. Instead, the ground was covered in ferns, horsetails, low-growing cycads, and mosses spreading across floodplains in dense green mats, interrupted by stands of tall conifers, ginkgo trees, and tree ferns whose fronds spread 15 feet across. By the Cretaceous period, roughly 130 to 100 million years ago, the first flowering plants were beginning their slow expansion across the landscape, but they were newcomers in a world already ancient, working their way into ecological gaps not yet dominated by older forms of life. Rain fell reliably. Rivers were wide and seasonal, flooding their valleys for months at a time and depositing the fine sediments that would eventually become the fossil-bearing mudstones and siltstones we now excavate. The Morrison Formation of the American Southwest, laid down between 148 million years ago, preserves one of the most detailed windows into Jurassic North American life ever found. Its layered deposits contain the bones of more than 70 distinct vertebrate species across hundreds of excavation sites. Here is the detail that almost no popular account emphasizes. The Morrison Formation is not a graveyard, it is a community. Every species preserved in those rocks occupied a specific ecological role. Every creature had neighbors, competitors, predators, or prey. The bones we find are not the scattered remnants of monsters roaming an empty world. They are the preserved members of a functioning, layered, interdependent ecosystem that operated with the same complexity as any living ecosystem on Earth today. Now watch what happens when you actually step inside it. Stand at the edge of a river on the Jurassic floodplain of what will become the American West, 150 million years ago, at the hour before dawn. The sky is still dark but warming. The air is heavy and warm, 25 degrees Celsius even in the early morning, saturated with humidity from the river nearby. Insects are moving already, enormous dragonflies with wingspans of 18 inches patrolling the reed margins. The river itself is wide and slow, maybe 400 feet across, braided into channels across a broad gravel floodplain. Then you hear it. Before you see anything, before the first light breaks across the tree line to the east, you hear a sound that carries through the ground as much as through the air. A low, resonant vibration. Not a roar, not a bellowing call. A deep, rhythmic pulse like a bass note struck somewhere below the range, where most sounds register as sound and instead register as pressure in the chest. A herd of Diplodocus is moving toward the river. They emerge from the tree line in a loose group of perhaps 12 to 15 individuals. The scale is impossible to fully prepare for. The largest adults reach 85 feet in length, with necks extending 26 feet ahead of their bodies and tails of equal length tapering behind them into thin whip-like tips. Each animal weighs between 10 and 16 tons. Their footfalls are deliberate and heavy. When the largest individual places a foot on the gravel, the ground compresses visibly and a low vibration carries outward in a radius of several feet. But they do not crash through the landscape. They move through it with a kind of practiced efficiency, stepping around the largest fern clusters, following a path that has clearly been walked many times before. The ground along their route is compacted down to hard earth, a trail worn through the undergrowth by generations of the same animals following the same path to the same water source. They need this water. A single adult Diplodocus required between 100 and 200 pounds of plant material per day to sustain its metabolic needs. That dietary requirement meant constant movement, constant grazing, and constant water intake. They did not stay in one place long enough to exhaust it. Fossil trackway evidence from multiple Jurassic sites in Europe, North America, and Africa shows that sauropods moved along established corridors, returning to known feeding zones and water sources in patterns that suggest learned routes passed down across generations. The feeding mechanics of sauropods were unlike anything alive today. They did not chew. Their teeth, where teeth were present, were designed for stripping rather than grinding. Peg-shaped tools for raking leaves and conifer needles directly from branches into the mouth. The actual breakdown of that material happened in the gut, assisted by gastroliths, smooth stones swallowed deliberately and retained in the stomach to function as grinding surfaces in a muscular gizzard. Multiple sauropod specimens have been found, with clusters of highly polished rounded stones in the stomach region, some collections weighing more than 10 pounds of stone in a single animal. Their necks were not raised like cranes, as early reconstructions suggested. Biomechanical studies of sauropod vertebrae and neck musculature indicate that most sauropods held their necks roughly horizontal or at a moderate upward angle, sweeping them side to side across wide feeding arcs without needing to raise their heads high. This posture allowed them to efficiently strip vegetation across large areas without the enormous energy cost of raising 2,000 pounds of neck to full vertical height. When they needed to reach upper canopy, they could, but it was not their default position. The juveniles travel in the middle of the group. This is not random. Sauropod juveniles were tiny relative to their parents. Hatchlings only 18 to 20 inches long, emerging from eggs no bigger than a cantaloupe. They grew at extraordinary rates, potentially reaching half their adult size within the first decade of life. During their vulnerable early years, they occupied a completely different ecological zone from the adults, living in the dense undergrowth where larger predators could not easily follow. But once they were large enough to travel with the herd, they moved in the protected interior positions, surrounded on all sides by adult bodies that represented the most effective predator deterrent on the landscape. And now you understand why the predators were watching from the forest edge. Allosaurus fragilis was the apex predator of the Morrison Formation ecosystem. It was a bipedal theropod reaching 28 to 32 feet in length, weighing approximately 1.5 to 2 tons, built on powerful hind limbs with 3-clawed feet that left distinctive 3-toed tracks at numerous Morrison sites. Its arms were shorter than its legs but heavily muscled, ending in 3 curved claws that functioned for grappling prey rather than delivering killing strikes. Its skull was long and narrow, reinforced internally with struts of bone that allowed it to absorb lateral impact forces, and lined with dozens of serrated teeth designed to slice through flesh rather than crush bone. Allosaurus was not a reckless charger. Bite mark evidence from sauropod specimens in the Morrison Formation tells a story of deliberate strategy. Allosaurus bite marks found on sauropod caudal and limb bones show a pattern consistent with repeated shallow strikes, followed by withdrawal, a wound and weight approach that allowed blood loss and exhaustion to accumulate in prey animals, many times the predator's own mass. This is the same strategy used today by Komodo dragons, by certain shark species, and by wolves working large ungulates. It is a behavior that minimizes the predator's own risk during encounters with animals that could kill simply by falling on the attacker or landing a single defensive blow, because the defensive armament in this ecosystem was real. Stegosaurus ungulatus traveled the same Morrison floodplains as Allosaurus, browsing in small groups at low elevations. Stegosaurs reached 26 to 30 feet in length despite their relatively small skulls and modest brains, and they carried a defensive system that paleontologists now have unambiguous physical proof was actively used. 4 large spikes projecting from the end of the tail, collectively called a thagomizer after a Far Side cartoon that became actual scientific terminology, were not decorative. A Stegosaurus tail spike has been recovered from the dorsal vertebra of an Allosaurus specimen lodged in a bone that shows evidence of infection and healing around the entry point. The Allosaurus survived. The encounter left its permanent signature in bone. That is a predator-prey negotiation conducted over millions of years of coevolution, preserved in 2 fossils, readable today as clearly as any text. The ecological middle layer of the Morrison world was dense and varied. Camptosaurus and Dryosaurus, smaller bipedal ornithopods, filled the niches between the giant sauropods above and the ground-level fauna below. Their slender builds and well-developed running limbs suggest animals capable of rapid flight when threatened. Multiple individuals of these species are regularly found together in fossil assemblages, consistent with group living strategies that gave individuals more sets of eyes to detect predators while each animal fed. In the sky above all of this, pterosaurs wheeled on thermal currents rising from the warm lowland landscape. Jurassic pterosaurs ranged from the size of modern pigeons to wingspans of 20 feet or more. They fished the rivers, scavenged carcasses, and caught insects over the open floodplains. Their hollow bones, air-filled and structurally rigid, made them extraordinarily light for their wingspans, and their brains show enlarged visual processing regions consistent with highly acute aerial hunters. The forest floor was equally alive. Small theropods moved through the undergrowth, hunting insects, lizards, and early mammals. Dryosaurus nests and feeding areas have been identified at multiple Morrison sites, showing concentrated bone material from multiple small vertebrates that appear to have been processed in place. And beneath even those small hunters, in the burrow systems threading through the roots of the cycad groves, the early mammals of the Mesozoic lived their hidden lives. These mammals were small. Almost all were smaller than a modern house cat. Many were mouse-sized or smaller. They were warm-blooded, covered in fur, equipped with hearing so acute they could locate insects in total darkness, and adapted for nocturnal activity in a world that belonged to other creatures during daylight hours. Their teeth were complex, capable of processing a diverse range of food sources from insects to seeds to small vertebrates. And that dietary flexibility was the most important survival trait they possessed, though they would not need it for another 85 million years. Now shift forward in time. Shift forward 85 million years to the late Cretaceous, to the age of Tyrannosaurus rex, and the final great chapter of the non-avian dinosaur world. The world has changed in fundamental ways. Flowering plants have now spread across the landscape in an explosive radiation that has altered every ecosystem they have entered. Insects are more diverse. Pollinators have co-evolved with angiosperms in relationships still continuing today. The conifer forests still dominate many regions, but broadleaf trees and flowering shrubs now share space in every environment the climate permits. The ecological complexity of plant life has risen dramatically, and with it, the complexity of the herbivore communities that depend on plant life. The continents have moved further toward their modern positions. The western interior seaway is still present but shrinking. The Hell Creek region of what will become Montana, Wyoming, and the Dakotas sits at the edge of that seaway, a warm, flat coastal plain of river deltas, oxbow lakes, dense subtropical forest, and open floodplains cut through by braided rivers. And in that world lives the most studied and debated land predator in the history of paleontology. Tyrannosaurus rex stood 12 to 13 feet tall at the hip. Its body length from snout to tail tip reached 40 feet in the largest confirmed specimens. Its weight is estimated between 8 and 14 metric tons depending on the individual and the methodology used, with current biomechanical models favoring the higher end of that range for adult animals. Standing in front of one is not an experience human vocabulary handles gracefully. The head alone was 5 feet long. That head was the central fact of Tyrannosaurus rex. It was not fast, not in the way popular culture imagines. Biomechanical studies of leg proportions, body mass distribution, and stress tolerance in the bones of T-Rex hindlimbs indicate that it walked at approximately 3 to 5 miles per hour and may not have been capable of true running at all, defining running as a gait with an airborne phase where neither foot contacts the ground simultaneously. At its maximum, it moved perhaps 10 to 12 miles per hour in short bursts. A reasonably fit adult human can run faster than that. But here's the part that changes the picture completely. T-Rex did not need to be fast. Its skull was built not for speed but for force, and the force it could generate was unprecedented in the history of land animals. Bite force estimates for Tyrannosaurus rex range from 7,800 to over 12,800 pounds per square inch in different studies, the highest measured or estimated for any land predator ever identified in the fossil record. Those jaws did not simply puncture, they pulverized. Coprolite analysis, the study of fossilized excrement, recovered material containing powdered bone, in quantities confirming that T-Rex routinely crushed and consumed bone as a regular dietary component, extracting the lipid-rich marrow from femur and vertebral cores that other predators left behind. Its olfactory system was exceptional. Endocast analysis of T-Rex brain cases, the fossil preservation of the brain's shape within the skull, reveals olfactory lobes proportionally enormous relative to overall brain size, larger than in most other known theropods, and comparable in relative terms to modern albatrosses, which can locate food sources from extraordinary distances using scent. Rex could almost certainly smell a carcass from miles away and track injured prey through forest and across open ground by scent alone. Its binocular vision was forward-facing and precise. The orbital architecture of T-Rex places both eyes oriented forward rather than to the sides, creating a large zone of overlapping visual fields that provide depth perception rather than panoramic threat detection. This is the eye arrangement of predators, not prey. It was also almost certainly feathered, at least in part. Fossilized skin impressions from T-Rex specimens show scales in some regions, but close relatives including Yutyrannus huali, a 30-foot tyrannosaur from early Cretaceous China, preserve clear evidence of a full coat of filamentous feathers. The exact extent of feathering in adult T-Rex is debated, but the presence of feathers in juvenile T-Rex and in close relatives makes it likely that at least some regions of the animal's body, particularly along the back and upper limbs, retained feathering into adulthood. The prey community T-Rex hunted was equally extraordinary. Triceratops horridus was the most common large herbivore in the Hell Creek environment, outnumbering T-Rex in fossil finds by a ratio of roughly 5-1. It reached 26 to 30 feet in length and 8 to 12 metric tons in the largest individuals. Its 3 horns, 2 brow horns reaching up to 4 feet in length, and a shorter nasal horn, were not decorative. They were made of dense bone with keratin sheaths that extended their effective length further still. Its frill was a massive bony shield extending backward from the skull, protecting the neck from attack from behind. Healed T-Rex bite marks on Triceratops bones have been found on multiple specimens, and conversely, Triceratops horn wounds and puncture marks on T-Rex facial bones have also been identified. These animals fought. Sometimes the prey survived, sometimes the predator survived. The fossil record of the Hell Creek is full of these stories, written not in words, but in healed injuries, preserved in bone across millions of years. The hadrosaur Edmontosaurus annectens reached 39 feet in length and may have weighed up to 4 metric tons. It traveled in large herds based on multiple bone bed deposits in Alberta and the Dakotas, showing mass mortality events where hundreds of individuals died together, probably during flooding events along river corridors. Their hollow crests in some species, or the fleshy nasal structures preserved in exceptional specimens of non-crested species, suggest a level of visual and potentially acoustic communication far more sophisticated than the simple herd animal of popular imagination. But the Hell Creek ecosystem extended far beyond the most famous species. Pachycephalosaurus, with its massive dome-shaped skull roof and elaborate head ornaments, occupied a medium-sized herbivore niche. Ankylosaurus, reaching 30 feet in length and armored across its entire dorsal surface with fused bony scutes and a club tail capable of shattering bone, was the most heavily defended land animal in the history of vertebrate life. Pterosaurs of this period were reaching their maximum sizes in some lineages. Quetzalcoatlus northropi had an estimated wingspan of 33 to 36 feet and stood as tall as a modern giraffe when on the ground, and the evidence for its behavior suggests it may have been a terrestrial stalker of prey rather than purely an aerial fisherman. The world that T-Rex and its contemporaries inhabited was not a simplified monster movie set. It was a fully functioning ecological community of dozens of large vertebrate species, hundreds of smaller ones, thousands of plant species, and millions of invertebrate species, all interacting in the complex interdependent web that defines a real ecosystem. Now step back from the community and look at the systems that governed reproduction and population. Dinosaur nesting behavior is one of the most important and most often overlooked aspects of the Mesozoic world. The discovery and excavation of the Egg Mountain site in Montana, beginning in the 1970s under paleontologist Jack Horner, fundamentally changed the understanding of dinosaur parental behavior. What Egg Mountain revealed was a nesting colony of Maiasaura, a large hadrosaur of the late Cretaceous, containing multiple nests arranged in a grid-like pattern with spacing between nests of roughly the body length of an adult animal. This spacing was not random, it was deliberate. Each nest was separated from its neighbors by exactly enough room for a parent to move around its clutch without stepping on adjacent nests. The nests themselves were bowl-shaped excavations of earth and vegetation, approximately 6 to 7 feet in diameter, each containing a clutch of 30 to 35 eggs, arranged in a circular pattern within the depression. The hatchlings found at Egg Mountain showed leg bone development inconsistent with immediate self-sufficiency. Unlike modern reptiles, whose hatchlings are mobile from birth, Maiasaura hatchlings had partially underdeveloped joints, suggesting they remained in the nest and were fed by returning adults for a period of weeks to months after hatching. Food material found in association with some nests includes crushed plant matter, consistent with adult foraging and return, the same behavioral pattern visible today in nesting birds. Maiasaura translates as good mother lizard. It was a name given by paleontologists based on what the fossils revealed, an animal that invested significantly in offspring survival beyond the moment of egg-laying. This was not a creature that buried eggs and walked away. This was a creature that returned, that fed, that protected. Other nesting sites across the world confirmed that Maiasaura was not exceptional. Oviraptor specimens recovered from the Gobi Desert of Mongolia were once thought to be nest raiders, having been found above eggs not initially identified as their own. Subsequent preparation of additional specimens showed that the oviraptor was not raiding the nest. It was sitting on it, arms spread in a brooding posture identical to that of modern birds, incubating its own eggs with body heat. The name, meaning egg thief, has never been officially changed, but the original interpretation was completely wrong. Feathered dinosaur specimens from the early Cretaceous of China, preserved in extraordinary detail by the fine-grained volcanic ash that buried them, show brooding postures with arms spread wide over egg clutches, the same posture used by modern turkeys and ostriches. The connection between theropod dinosaurs and modern birds in terms of reproductive behavior is not theoretical, it is preserved in rock. Migration patterns governed the movement of large herds across the Mesozoic landscape on seasonal cycles, as they govern large animal populations today. Ceratopsian bone beds in the Dinosaur Park Formation of Alberta are among the most dramatic evidence for this. Single bone bed deposits containing the remains of hundreds to thousands of individual Centrosaurus apatus, a horned ceratopsian roughly 18 feet long, record mass mortality events during river crossings. The pattern of death, the mixing of individuals of all ages and sizes, the evidence for rapid burial by flood sediment, and the directional consistency of the bone alignment are all consistent with large herds moving across the landscape in seasonal migration and suffering catastrophic mortality at river crossings. These were not chaotic creatures wandering randomly across an empty world. They were participants in ecosystem rhythms as structured and predictable as the annual wildebeest migration across the Serengeti, or the caribou migrations across the Arctic tundra, or the biblical nomadic cycle of movement between seasonal pastures. The Mesozoic world operated by the same fundamental principles that govern all living systems. Energy flows from sunlight through plants, through herbivores, through predators, through decomposers, and population movements track energy availability across the landscape. But that world was not static. It was under pressure long before the final catastrophe. The Deccan Traps are a vast volcanic province in what is now central India, formed by an enormous outpouring of basaltic lava that began approximately 66.25 million years ago and continued for several 100,000 years. The volume of lava produced was extraordinary, covering an area roughly the size of modern India to depths exceeding a mile in some places, and releasing enormous quantities of sulfur dioxide and carbon dioxide into the atmosphere over that extended period. Climate models suggest that Deccan Traps volcanism was already causing significant environmental stress during the final stages of the late Cretaceous, potentially contributing to a gradual decline in some dinosaur species diversity in certain regions before the final impact event. Paleontological evidence from the Hell Creek Formation itself shows a complex picture in the final 2 million years of the Cretaceous. Some studies suggest a decline in hadrosaur and ceratopsian diversity in the upper Hell Creek beds, while others find evidence of a robust and diverse fauna right up to the KPG boundary. The debate remains scientifically active. What is not debated is what happened at the boundary itself. The Chicxulub asteroid impacted what is now the Yucatan Peninsula of Mexico approximately 66.043 million years ago, a date established through radiometric methods with high precision. The impactor was an object estimated between 6 and 9 miles in diameter, composed of carbonaceous chondrite material and traveling at approximately 45,000 miles per hour at the moment of contact. The kinetic energy released upon impact was equivalent to roughly 1 billion atomic bombs of the Hiroshima yield, detonated simultaneously at the same location. The immediate blast radius was total destruction across hundreds of miles in every direction. The impact vaporized the impactor entirely and excavated a crater approximately 93 miles in diameter and 12 miles deep in the first seconds of contact. Enormous quantities of sulfate-rich rock were vaporized along with the carbonate seafloor at the impact site, producing sulfur dioxide in quantities sufficient to cause significant acid rain deposition across the planet within weeks. Beyond the immediate blast zone, material ejected from the impact at hypersonic velocities re-entered the atmosphere across the entire planet within hours. This re-entry heating, as billions of superheated particles descended through the atmosphere, raised surface temperatures sufficient to ignite forest fires on a global scale. The global charcoal and soot layer, preserved in sediments at the KPG boundary worldwide, represents the remains of those fires. Within days, the combination of impact dust, soot from wildfires, and sulfate aerosols had begun blocking sunlight from reaching the surface. Photosynthesis, the process by which plants convert solar energy into chemical energy and form the foundation of every food chain on Earth, began failing on a global scale. Within weeks, global surface temperatures began dropping sharply as the atmospheric particulates reflected sunlight back into space. The impact winter that followed lasted an estimated 3 to 10 years, based on models using the estimated quantity of material injected into the stratosphere. For the largest animals on Earth, animals that required hundreds of pounds of vegetation per day, that required stable thermal environments for reproductive cycles, that required the functioning ecosystems of an entire world, 3 to 10 years of darkness and cold and collapsing food chains was an impossible situation. No behavioral flexibility, no intelligence, no evolutionary adaptation accumulated over 165 million years could overcome the disappearance of the sun. Approximately 75% of all species on Earth were extinct within a geologically brief period following the impact. Every lineage of non-avian dinosaur that had survived to the end of the Cretaceous was gone. Every sauropod lineage, every large theropod lineage, every ceratopsian, every hadrosaur, every ankylosaur, every pachycephalosaur, the magnificent, complex, layered world that had been building since the first archosaurs diversified in the Triassic, was dismantled within an interval that, measured against the 4.5 billion year age of the Earth, was essentially instantaneous. But survival was not zero. What survived was defined by a precise set of characteristics. Small body size was the single most important factor. Small animals required less caloric intake and could survive on the compressed, reduced food resources that persisted through the impact winter. Dietary flexibility was the second most critical factor. Animals capable of eating a broad range of food types, insects, seeds preserved in soil, aquatic prey, carrion, fungi growing on the enormous quantities of dead organic material, had options. Animals specialized to a narrow dietary range had none. Burrowing and aquatic habits provided thermal insulation. Reptiles hibernating underground, freshwater fish and turtles in rivers and lakes insulated by water, crocodilians capable of surviving long periods without food. These animals had physical refugia that terrestrial animals dependent on surface conditions did not. Certain bird lineages survived, specifically those with the dietary flexibility to subsist on seeds. Seeds do not require photosynthesis to remain viable. A seed stored in the soil represents chemically packaged energy that can survive years without light. Small birds capable of finding and processing stored seeds had a food source available through the worst of the impact winter that no large herbivore could access. Early mammals, the small nocturnal insectivores and omnivores that had spent 165 million years living in the margins of the dinosaur world, survived. Their small bodies, diverse diets, burrowing habits, and rapid reproductive rates gave them every characteristic that defined survival in the post-impact world. And here is the most extraordinary fact in the entire story of the dinosaur world. The lineage did not end. Avian dinosaurs, the birds, did not go extinct. They went through a severe bottleneck, with many lineages lost in the extinction. But the surviving lineages recovered, and over the following 66 million years, they diversified into every ecological niche available to a warm-blooded, winged, highly mobile vertebrate. Today, there are approximately 10,500 recognized bird species distributed across every continent on Earth, including Antarctica. They occupy ecological roles ranging from large cursorial predators to tiny aerial insectivores to deep-diving aquatic hunters to nocturnal forest specialists. Every single one of them is a dinosaur, not metaphorically, not by analogy, taxonomically, biologically, and by direct evolutionary descent. Birds are avian theropod dinosaurs, members of the clade Dinosauria, in the same way that bats are mammals and sharks are fish. The hollow bones of a sparrow are the hollow bones of a theropod. The wishbone of a chicken is the fused clavicle of a theropod. The scales on a bird's feet are the scales of a theropod. The air sac system that makes bird respiration so extraordinarily efficient, allowing them to extract oxygen from air even at extreme altitudes, is the same air sac system visible in the fossil vertebrae of large theropods like T. rex, where the hollow vertebral chambers once filled with air sacs are still visible in the rock. The feathers on every living bird are the feathers that evolved in small theropods in the Jurassic and Cretaceous, initially for insulation, then for display, then adapted for flight in the avian lineage. We know this not from theory, but from the extraordinary fossil discoveries of the past 3 decades in China, where fine-grained lacustrine deposits have preserved feathered theropods in hundreds of specimens, showing every stage from simple filamentous downy covering to fully asymmetric flight feathers identical to those of modern birds. There is a passage in the book of Job, in the 38th and 40th chapters, where a voice from the storm asks a man whether he was present when the foundations of the earth were laid, whether he knows where light comes from or where darkness retreats. And then the voice describes 2 immense creatures, Behemoth with bones like iron, with a tail like a cedar tree, and Leviathan, a creature that breathes smoke and out of whose nostrils comes flame. Ancient scholars debated whether these referred to a hippopotamus, an elephant, a crocodile. None of those identifications quite works. The hippopotamus does not have a tail like a cedar tree. The elephant does not move rivers with its breathing. But across the ancient world, fossil bones were encountered regularly. They eroded from cliff faces, they protruded from riverbanks, they turned up in quarried stone. The enormous bones of extinct megafauna, and in some regions the bones of dinosaurs and other Mesozoic animals, were found and incorporated into the explanatory frameworks of whatever civilization encountered them. In ancient Greece, fossil skulls of extinct elephants, with their large central nasal cavities, gave rise to the Cyclops legend. In ancient China, dinosaur and other large vertebrate fossil bones were described as dragon bones in medical texts going back at least to the 4th century AD, and were ground into powder for medicinal use for over 1,000 years. Native American tribes in the American West and Great Plains encountered the enormous dinosaur and mammal bones eroding from the Badland formations, and developed cosmological frameworks to explain creatures that no living person had ever seen. The impulse to understand what the Earth contains, to make sense of remains from a past that exceeds living memory or written record, is not a modern invention. It is ancient, and it has driven human investigation of the natural world in every culture and in every era. What the paleontological record provides today is the clearest answer yet to a question human beings have been asking since they first found a bone they could not identify. The Earth is older than any single human account of it. The living world we inhabit is the survivor of multiple catastrophes, multiple collapses, multiple rebuildings, from whatever complexity managed to persist through the worst of each event. The world of the dinosaurs was not a failed experiment. It was a success of staggering proportions. 165 million years of ecological dominance. Creatures of every size, from a hummingbird to an 8-story building. Ecosystems of complexity that took tens of millions of years to build, and in some ways have not been equaled since. The diversity of large herbivore species in the late Cretaceous of North America exceeded the diversity of large herbivore species in any modern ecosystem on Earth. And all of it was ended in an afternoon, by a rock from space, by a random intersection of orbital paths that had nothing to do with the health or weakness or fitness of the world it ended. The mammals that survived, the small, nocturnal, ecologically marginal creatures that had lived in the footnotes of the Mesozoic world for 165 million years, emerged into a planet stripped of complexity and began, slowly and then rapidly, to fill it. Over the next 20 million years, they diversified into every large body size category the dinosaurs had vacated: horses, elephants, whales, bats, primates. All of these lineages emerged in the Paleogene as mammals occupied the ecological architecture that the non-avian dinosaurs had built, and then, in a geological instant, vacated. Human beings are the product of that process, not in a distant, abstract sense, but in a direct biological line. The primate lineage that eventually produced Homo sapiens diverged from other mammalian lineages within the first few million years after the KPG extinction. Our earliest ancestors were small, forest-dwelling, insect-eating primates, no larger than a modern squirrel. Every characteristic that makes us human, our large brains, our social complexity, our language, our capacity to build civilizations and write books and ask questions about the world, emerged from a lineage that survived the end of the dinosaur world by hiding in burrows and eating insects in the dark. The dinosaurs did not go, they adapted, they shrank, they flew. The next time you watch a heron stand motionless at the edge of a river, patient, head tilted to track movement in the water below, understand what you are looking at. You are looking at a descendant of the theropod lineage, an animal whose ancestors walked the Morrison floodplains 150 million years ago, an animal whose bone structure, respiratory system, reproductive biology, and behavioral toolkit trace in an unbroken line back through the Cretaceous extinction and into the deep past. The heron's patience is not an accident. It is the patience of a lineage that has been hunting on this planet for a very long time. Every crow problem-solving in a city park, every peregrine falcon stooping at 240 miles per hour above a modern city, every albatross crossing an ocean for 3 years without landing, every emperor penguin standing through an Antarctic winter in total darkness. These are all dinosaurs. They are the ones that made it, and they have been making it continuously for 66 million years since the impact winter ended and the sky cleared and whatever was left of the world began again.